this video, we'll show some other interesting instructions of the x64 architecture belonging to the general purpose group. Some of them are classified as miscellaneous instructions. Input I/O instructions allow the processor to transfer data between the accumulator register and the peripheral device. Peripherals in x64 architecture are visible in a separate address space, 64 kilobytes in size. Each address of a peripheral is named a port. Depending on the peripheral hardware implementation, the port represents the address of a byte, word, or double word. A peripheral device can be addressed directly or indirectly. Direct addressing uses an 8-bit constant as the peripheral address named in x86 I/O port, and it addresses only the first 256 port addresses. Indirect addressing uses the DX register as the address register, enabling access to the entire I/O address space of 60K addresses. The IN instruction reads data from a port to the accumulator. The OUT instruction writes the data from the accumulator to the port. The size of the accumulator determines the size of the data to be transferred. It can be AL, AX, or EAX. The I/O instructions also have string versions. Instructions to read the port to a string are ins, insB, insW, and insD. Instructions to write a string to a port are outs, outsB, outsW, and outsD. In a string I/O instruction, the port is addressed with the DX register. Rules for addressing the memory are the same as in the string instructions. Flag control instruction set or clear the selected flag in the R flags register. We can only control 3 flags directly. The carry flag can be used in conjunctions with the rotate with carry instructions to convert the series of bits into the binary encoded value. The STC is to set, CLC to clear, and CMC to complement the carry flag. The direction flag DF determines the direction of the modification of index register RSI and RDI when executing string instructions. If the DF flag is clear, with the CLD instruction, the index registers are incremented. If the DF flag is set with the STD instruction, the registers are decremented after each iteration of the string instruction. The interrupt flag IF enables or disables hardware interrupts. If the IF flag is set with the STI instruction, the hardware interrupts are enabled. If the IF flag is cleared with the CLI instruction, hardware interrupts are masked. The flags register can be pushed onto the stack and popped afterwards. This can be done inside the procedure, but also to test or manipulate bits in the flag register, for which modifications are not supported by the special instructions. The push F pushes the flags register, the push D pushes the EF flags register, and the push FQ pushes the R flag register onto the stack. The pop F pops the flags register, the pop FD pops the E flag register, and the pop FQ pops the R flags register from the stack. There is also a possibility to copy SF, ZF, AF, PF, and CF to the HAH register with the LHF instruction and store this flag back from HA with the use of the SAHF instruction. The NOP instruction performs no operation. The only result is incrementation of the instruction pointer. In reality, it is an alias to the instruction exchange EAX. To test the behavior of the system software in case of the appearance of an unknown opcode in the instruction stream, the instruction set includes the undefined instructions. The UD and UD1 instructions can have a source operand, register or memory address, and a destination operand, register. Operands are not used. The UD2 instruction doesn't have an operand. Executing any of undefined instruction results in an invalidation opcode exception, #UD thrown. The CPU ID instruction provides processor identification information. It operates similarly to the function, with the input value sent via an accumulator, EAX. Depending on the EAX value, gives different information about the processor. The requested information is returned in processor registers. For example, if AEX is 0, it returns the vendor information string. For example, genuine Intel or for Intel processor and authentic AMD for AMD models in ECX, EDX, and EBX registers. The load effective address instruction is very often used to load the register with the actual address of a variable. The LEA instruction calculates the effective address as the result of the proper addressing expression and stores the result in the destination operand. We can store the effective address in a single register to avoid complex address calculations inside a loop. Because the LEA instruction adds source arguments, it is sometimes used instead of the add instruction. By using a complex addressing mode with scaling, it can even replace multiplication. Please watch other videos about instructions. For a detailed description of instruction groups and instructions, please refer to our Purple book and AMD and Intel documentation.